let's go with the second part of the day. And we have the session 3. We will start with discussing Irene Botosaru and discussing the paper Difference in Differences, Estimators with Repeated Cross Sections, Staggered Timing, and Heterogeneous Treatment Effects. By authors Partha, Edward Norton, Jeff Woodridge, and Jeff Saville, and you know them, so I'm going to say institution. So thank you.
Thank you. Thank you to the organizers for reaching out. This is my first AQ, so let's see how it goes. So indeed, this is what the paper is about. I just want to say this session, I think, is about, here we take no anticipation and parallel trends as given, and we do not question them. Here we worry about other things, and you're going to see what we're going to be worrying about here. So here we're going to be worrying in particular about cross sections, repeated cross sections, so not panel data. And then we're going to be also worrying about time varying covariance. Okay, so these are going to be the two main issues that I will be discussing related to this paper. So a very, very quick summary of the paper. So yes, we're going to be in a differences in differences setting. There's going to be a treatment that's going to be implemented at the group level. It's going to be implemented in a staggered way, staggered across groups and across time periods. And we will be allowing for heterogeneous treatment effects, heterogeneous at the group level and at the time level. The contribution of the paper is essentially to extend the extended two-way fixed effects estimator of Woolrich 2021 to repeated cross sections and time varying covariance. Okay, so the extended two-way fixed effects estimator of Woolrich allows for panel data and time invariant covariance. Here we're extending the applicability of that method to repeated cross sections and time varying covariance. I would say that the main focus is really maintaining ease of computation and addressing the issue of time varying covariance when we have repeated cross sections. So this is my one slide summary of the paper. And now I'll go into the details, then I'll present my discussion. So I'll talk about some of the, what I perceive as being some of the potential benefits and some maybe of the potential challenges, or maybe like open questions. And then I'll present a robustness check for one of the applications based on my own work in the area. So some of the details. So the paper proposes the FLEX estimate. So FLEX stands for Flexible Linear Model Estimated by OLS with Covariance X. Okay, this is FLEX. And FLEX extends the extended two-way fixed effects of Woolrich to repeated cross sections and time varying covariance. As such, it essentially inherits the properties of the Woolrich estimator. In particular, the parallel trends assumption is going to hold for all time periods, not just for one of the previous pre-treatment time periods, but rather for all of them. And then the clean controls are going to be formed by both never treated groups and not yet treated groups. Okay. It's also going to inherit the computation, so it's going to be very simple to compute. It's also going to inherit efficiency, so the estimator is going to be efficient under a linearity assumption that I'll be presenting later, and under the Dowles-Markov assumptions. Okay? So these are all very nice properties of the estimator. The emphasis in the paper is really on the time-varying nature of covariance when you have repeated cross-sections. And I actually like this quite a lot because it goes a little bit against, not against, but it has an emphasis that has not really been made previously in the literature, particularly on, in work on differences in differences repeated cross-sections, which also includes some of my own work. We have always assumed that the covariates do not really change, even if the different individuals are sampled at different time periods. So I think that this is a very nice contribution of the paper. The paper, I believe, is motivated by ease of computation, as well as the time-varying nature of the covariates. And the reason for which I say this is because essentially repeated cross-sections can be worked with, the Callaway and Santana estimator allows for repeated cross-sections. The Borusiak et al. Framework also allows for repeated cross-sections. And time-varying covariates we have also seen in Borusiak et al., Gardner et al., and Getano. And by the way, like if there is a plus, this means that it's a working paper. Okay, so two of the working papers also use time-varying covariates. So the Borusiak et al. Approach allows for both repeated cross-sections and time-varying covariates. Again, the focus of this paper is really on ease of computation when you have these two situations. And I'll come back to the Borusiak et al. In my discussion. So now I'll show you the setup. So here we have T time periods indexed by little t. Q is going to be the earliest period of implementation. So the treatment can be implemented at time period 2, 3, and so on. So we're going to call that Q. The treatment is going to be implemented at the group level, and the groups are going to be indexed by little g. Okay, and 1 to overline little g essentially is going to denote a group that is eventually treated. In my next slide, I'm just going to say that if G is in calligraphic tree, that means that the group is eventually treated. Okay. The groups can receive the treatment simultaneously, and they can form cohorts based on when they first receive the treatment. And a cohort is going to be denoted by little c, and obviously c is going to be either like it's going to go from Q plus 1. So if you have a bunch of groups that get treated at time period Q, then they form cohort C. Okay. So an important assumption here is that an individual can belong to one and only one group, and that if your group is eventually treated, then all the individuals in that group are treated. Okay, so if you want to think about this, this is universal implementation at the group level. So everybody in a group gets treated, and they get treated at the same time. Here in blue, so whatever is in blue, this is the notation that I'm going to take with me in the next slide. So RG indicates group membership. So if individual I belongs to group G, then RG is going to be equal to 1. And this is essentially the treatment indicator. So the treatment is going to be IU in group G. Okay. YTG is the potential outcome at time t if individual I belongs to group G. And YT infinity is the potential outcome at time t if individual I belongs to a group that is untreated or that never gets treated. And XT are obviously the covariates. The parameter of interest is the usual ATT. So this is the average treatment effect if you belong to group G, and is defined as usual. So it's the difference between the potential outcome of being in group G minus the potential outcome of not receiving the treatment, conditional on the individual being in group G. The proposed solution relies on standard assumptions in this literature. So we have SUDVA. So my potential outcome depends only on me being in group G. Doesn't depend on anybody else's treatment indicator. We have the no anticipation assumption, and here we don't question it. Here we really assume that before the implementation of the treatment, we do not have any changes in behavior, or we have no causal effects before the implementation of the period. We allow for time varying covariates, but of course we have to assume that the variation over time is exogenous to the treatment. Okay? So the XT evolve exogenously from the treatment. And then we also have a conditional common trend assumption as well as a functional form assumption lumped into one. And that assumption is the following. So I know it's a full slide here, but what the assumption says is that for all time periods from 2 to cap t, the conditional expectation function of the potential outcome without the treatment, conditional on the entire sequence of treatment indicators and on the covariates of time t, this conditional expectation function can be separated into two parts. Sorry, I'm trying to use this. So it can be separated into two parts here, even in the brackets. A part that depends only on group effects and on the interaction with the covariates. So you see here RG, so beta G and gamma G are group effects, as well as group effects interacted with the covariates. And then the second part depends on the time effects and interaction with the covariates. Okay? So this is where the extended two-way fixed effects kicks in, because in a way, we are keeping the group and the time effect separate. And the linearity comes in because everything here is linear in the parameters of interest. You can see here that essentially we have a parallel trends assumption given here, because the average trend in the control state, so the difference between these two potential outcomes for all time periods t, do not depend on the treatment indicator. And so this is my usual parallel trends assumption here in this assumption. Just wanted to make sure that, yeah. I want to draw your attention to something, because I'm going to come back to this later, as being actually one of the interesting benefits of this paper, of this assumption, is that essentially the assumption is making an assumption on the way that the covariates affect the outcome without the treatment. Okay, so essentially here, if you look at this, this expression here, you're going to see that the covariate effects are separable into group effects and time effects. And depending on your view, this can be seen as a strong assumption because I'm not allowing for interactions between group and time effects of the covariates. But at the same time, this is going to have a testable implication that I think is quite nice. And I'll get back to that in my discussion. But essentially, under those four assumptions, the main result of the paper can be, I think, can be summarized in this slide. So under those four assumptions, we can get an estimating equation that says the following thing. That if you take the outcome for individual I in cross-section T, and you regress it on group effects and group and covariate effects, time effects and covariates, a group time trend, so this is group indicator times time indicator, and a group, so again, the treatment indicator, so this is group indicator times time indicator, and the covariates that are demeaned at the group level, then the ATT, the sequence of ATTs, so the sequence across groups and time, is going to be recovered by this parameter here. Okay. So in my opinion, this is the main result of the paper that essentially says that under those four assumptions, we can do pooled OLS and get a sequence of ATTs that vary by group and time. There are additional results in the paper. So the paper also talks about how to perform aggregation of these ATTs, either across groups, across time, or both. Here I only presented the estimating equation with lags, but of course there's also an extension to leads. And the paper also presents a two-step imputation approach that essentially produces the same estimate as the estimate from the pooled OLS. The paper also presents two applications that are done with publicly available data because those are repeated cross-sections, so that was very nice. One of the applications looks at the effect of the punitive prenatal substance use policies on women's mental health, and then the other one looks at the right to work laws on earnings. Okay. I think I should breathe it. Talking faster than during my repetitions at home. Okay, so discussion. So I'll first start with the benefits. So first of all, I think that this is, so one of the benefits is that essentially you can use standard software to implement this estimator. So you don't need any special package, you don't need to code anything, you can just use standard software. You can incorporate time varying covariates, again, that are exogenous to the treatment in a very straightforward way. The focus of the paper is explicit on repeated cross-sections. So it's not just an afterthought put in an appendix. So it's really repeated cross-sections of time varying covariates. And then under the linearity assumption and the Gauss-Markov assumptions, particularly homoscedasticity and serial lack of serial correlation, you get efficiency of this estimator. Now, the linearity and the separability of the covariate effects turns out that they have a testable implication when you have three pretreatment time periods in two different groups. And I haven't seen this in the paper, and I also haven't seen this in differences papers that impose a linearity assumptions. It seems that people, so this is a strong assumption, but because it's a strong assumption, it has testable implications, and I think that we should be able to exploit that assumption and these testable implications. So I'm going to show you what I mean by this testable implication. So if you remember, this is the equation for the linearity of the conditional expectation function of the potential outcome without the treatment. If you have three pre-treatment time periods and two different groups, you can first look at the average outcomes across groups at the same time period. And then you can look at the difference in this average across two different time periods. And then you're going to notice that the difference in average outcomes across groups over the pre-treatment time periods, these three pre-treatment time periods, that is going to be proportional to the change or to the difference in covariates over the same pre-treatment time periods. Okay? So yes, okay, the assumption is strong because it implies this proportionality restriction, but at the same time, if we have three pre-treatment time periods, we can just go ahead and test this via an F-test or a wall test. So at least it can provide some type of suggestive evidence that this assumption holds or doesn't hold in our data. And so I think that actually this is the good aspect of this assumption. Potential challenges, the linearity assumption itself. So first of all, I think that the linearity assumption makes it a bit difficult to compare this paper to the estimators proposed by Callaway and Santana, for example, or more generally to the estimators that I call subgroup estimators. So like the Sun and Abraham or the stack differences in differences. And the reason for which I say this is because at least in the Callaway and Santana approach, the authors are doing a doubly robust estimation procedure. So they're trying to explicitly not impose a linearity assumption. And so then I started thinking, like, what if the Callaway and Santana approach also impose a linearity assumption? What will we gain then in terms of standard errors? Okay, so also it turns out, so I found this paper, Harman 2024, there's a working paper 2022, but he updated it recently. So he actually shows that the Callaway and Santana estimator is efficient under serial correlation for a very short post-treatment period. So if you look at the ATT in a very short horizon after the treatment. So I kind of find that this is interesting. So the linearity assumption and the Gauss-Markov assumptions essentially make it a little bit more difficult to compare this paper to, say, the Callaway and Santana estimator. But then I think that the Borusiak et al. Approach is the actual competitor to this paper. Because the Borusiak et al. Imposes linearity, looks at repeated cross-sections, and allows for time-varying covariates. And for example, we know, I think also Jeff Woodridge has some work on this, and we know that essentially for the panel case with no covariates, the extended two-way fixed effects and the Borusiak estimate produced the same numerical answers, and that both of them are efficient under Gauss-Markov, so they're essentially the same estimator, the same efficient estimator in the class of linear estimators. But for example, we do not know anything about how Flex, for example, would compare to the Borusiak et al. With repeated cross-section. So I think that a comparison with the Borusiak would actually be its own contribution to the literature because we have no idea how these two estimators compare in the case of repeated cross-sections, with or without covariates. The linearity assumption is also a little bit tricky, I think, because one of the applications allows for count outcomes. So those are the days of good mental health of pregnant women. And so I was thinking that maybe a nice extension, which I think would also be really straightforward, would be essentially to allow for a generalized linear model. So just put an exponential function around your linearity. Of course, then you probably have to drop the L from flex, but then you would be extending your procedure to nonlinear. And I think I think this is doable. The other potential challenge, I actually think it's the actual time variation in the covariates, because now we have to be a little bit more careful when we use our time-varying covariates. And so then I was thinking that maybe a possible thought experiment that we could use is to think, okay, suppose that instead of having repeated cross-sections, we had panel data, and we observe the same covariates that we observe in our repeated cross-sections. Would those variables be time-varying if we observe them in the panel data? And if the answer is no, then maybe we have suggestive evidence that the time variation may actually be due to sampling of the individuals across time, as opposed to endogenous variation. But then, of course, we have to make sure that the treatment itself does not induce movement of individuals across time periods. And then I had some thoughts about how to maybe the authors would want to consider providing a little bit more conversation about the covariates chosen in the applications, and I can talk to you later. But essentially, I also thought that it would be very nice to provide some formalism of the assumption of what it means for the covariates to have time variation that is exogenous. Because I was thinking, would they be mean? Like, would you need them an exogeneity in the mean of the covariates, or a statistical exogeneity? Would it be conditional or anything, or unconditional? So I have some thoughts and some further questions about that. But yeah, I think it would be nice to formalize the assumption. And finally, but this is also shared, so there are many parameters to estimate here. So if you think about the estimating equation, we're going to have, depending on the number of groups, number of time periods, and covariates, we're going to have many right-hand side variables, because we have to allow for interactions between groups, time, and covariates, the values that the covariates take. And it is possible to decrease the number of parameters. We can either impose equality assumptions, like in Woodridge or in Borusiak, But then of course that can lead to bias if the quality assumptions are misspecified, or to inefficiency in case there's just not enough restrictions that are imposed. Or we can use a data-driven approach from the high-dimensional literature, so we can look into ridge regression or lasso. And here's a Faletto, this paper that essentially proposes a way to shrink the number of parameters for the extended two-way fixed effect. So, and I think that this is up for grabs. And it would also just be like really easy to implement. It's kind of like a lasso penalty function that you add to an OLS, and efficiency would also be preserved. This is something that I found worrisome, but also extremely interesting and intriguing. Okay? I'm a theoretical econometrician. When I saw this in the paper, I essentially just wanted to talk only about this. So the authors noticed that in the application, the overall ATT, the estimate, shrinks to 0, while the standard error of the ATT stays the same or decreases. Okay, so bias variance trade-off doesn't apply, which is very bizarre. So this happens as the number of interactions with X increase. I a priori don't have. I was very surprised by this. I was expecting a bias variance trade-off to kick in. That didn't happen. So then I'm thinking, I don't know whether this is connected to maybe having too many covariates. I do not know. But it could also happen because maybe there is multicollinearity between the covariates, in which case I would call that spurious shrinkage. Or it could happen because maybe the outcome variation in the outcome variation is actually explained by the covariates, in which case I would guess that's like real shrinkage, because then you're taking care of the omitted variable bias. There are a few diagnostics that I thought of that maybe one could try. So we can compute the condition number of the matrix of covariates. If that's above a particular number, then we have multicollinearity. We can compare nested models, or even look at k-fold cross-validation. So there are particular diagnostics that one can do to get a sense of this. I would run simulations, but then I could also look at the power and the coverage rates of the estimators. And also, like, I realized that I don't have a good sense of the asymptotics. Like, for example, I didn't realize if I needed G, the number of groups to go to infinity or not. Maybe not, but I do not know. So I think I would also like to see a little bit of that or talk to you. And I'll try very fast to do a little bit of a robustness check here based on my own work. So for one of the applications, the authors look at the effect of right to work laws on earnings. And here I'm going to be implementing what I call the FAT, forecasted average treatment, as a robustness check for particular, for non-stationarity that may exist in earnings, serial correlation, or heteroscedasticity. So I'm going to start from the fact that all the individuals in a treated state are treated. So then I'm going to start from the fact that if I aggregate the data to the state level, I'm going to have a bunch of groups that are treated. In particular, I'll have 5 treated groups. And then I'll also have some states that are not treated. So those are going to be my control states. So what will I be aggregating? I'll be aggregating the data. So here, the data comes from CPS. So this is CPS data on hourly earnings. I'll be aggregating that at the state level, and then I'll be implementing FAT. What is FAT? So for each treated group, I'll be doing an extremely simple regression. I'll take the pre-treatment outcomes for each treated group, and I'll regress that on a polynomial in time. So polynomial in time regression. I'll get the estimates, and then using those estimates, I'll forecast the counterfactual. So each treated group is going to have a counterfactual, and then the ATT, which is my FAT, so the forecasted average treatment effect, at time t plus h, so at horizon h, is going to be the average over the treated group of the difference between the observed outcome and the forecasted counterfactual. Why would I be interested in doing this? Well, in this paper, we show that essentially if your potential outcome has non-stationarities, so if it's a unit root, or if it's a mean stationary process, so think AR1, ARQ, where you don't have to know the Q, And if on top of that, say the AR parameter is group specific, or if your potential outcome has either a non-stationary component or a mean stationary component, and if it also has group specific time trends, then FAT is going to be robust to all of those specifications. We know from the earnings dynamics literature that earnings in general has these two components, either unit root, mean stationary, and that on top of that, it also has linear trends or non-linear trends. So I thought that this would be kind of like a nice robustness check to do here. So FAT also doesn't need any control groups. You can use the control groups if you want to, because then you can get rid of the potential common shock that exists. And you can also apply FAT all the way to the last period once everybody has gotten treated, because again, FAT doesn't need control groups. And although this sounds like a time series procedure, because we're really focusing on these non-micro properties of our processes, FAT actually works with very short t. In order not to produce any type of trivial answers, we need at least 2 pre-treatment time periods. Okay, and I'm doing this because again, I want to check if flex for this particular application is going to be robust to the parallel trends assumptions that has to hold for all pre-treatment time periods, the linearity assumption, and to the serial correlation or potential unit root in the earnings. So I'm going to use data on 5 different states. The data is 2008, 2017. The paper uses covariates. These covariates, I'm only going to focus on the sample of women. I use the sample of women because the Partha et al. 2023 paper shows that it was mostly women's earnings that decreased once these laws were implemented. So now I'm going to show you data, the data on those 5 states. So here we have Indiana, Michigan, Wisconsin, West Virginia, and Kentucky. Horizontal line is time, so 2008 to 2018. Dashed line is the time when the law was implemented, the year when the law was implemented. You see that it's staggered across the states. Vertical line, so the y-axis shows you the averaged earnings at the state level. Okay. And the dots show you the data. Okay, so the dots, so this is the pre-treatment, these are the pre-treatment averages, and the black dots to the right of the dashed line are the post-treatment outcomes. And the red crosses are essentially the forecasts based on a very simple quadratic polynomial. Okay, I didn't do any type of more detailed work, as maybe I should have done. I just fit a quadratic polynomial to all the states, and then I obtained the forecast based on that. Okay. One could argue that there is some non-stationarity, like for example here, maybe I shouldn't be using all pre-treatment time periods, but I did. So here are the results. So this is flex with the entire sample for the case of no covariates, right? So there's a decrease of about 67 cents per hour. And here's FAT for the entire sample. At horizon 2, I get 74 cents minus. And when I use the entire sample, so when I use also the control groups pretending that they were treated in 2012 to see if I can get rid of some common shock, I see that now I get something that's much closer to flex than just my FAT estimate. Okay. So I interpret this in a positive light, and I say, yeah, it looks like like flex here was actually robust against like all these linearity and serial correlation and other stuff that can potentially mess up the efficiency result. Okay. And then I also wanted to see what would happen if the Norton et al. Results would also be reflected in my FAT estimates, and I see that, yeah, women definitely got more affected than the entire sample, and then women older got a little bit more of a cut in their earnings. I do want to mention here that these comparisons maybe are not quite fair because flex uses repeated cross sections and it's like 500,000 observations, while FAT uses only 5, n is 5. Okay. We do need n large for our asymptotic normality results, but nonetheless, we do get statistical significance with FAT as well. The good news is flex, good. It passed my robustness check. So in conclusion, think Flex, yeah, I was also happy. I was also happy with that. So, because I didn't want to not, yeah. So Flex, I think it's very nice. It extends the applicability of the extended two-way fixed effects estimator. It extends it to time-varying covariates and repeated cross-sections. And so now essentially publicly available data sets with repeated cross-sections can be essentially used. The implementation is straightforward. I think it would be nice to run some diagnostics to understand why this shrinkage happens. And then if a concern, of course, the extension to nonlinear models, I think it's there and it should be really straightforward. The testable implication, that also should be straightforward, done by a wall test. And then, of course, if a concern, one can also decrease the number of covariates on the right-hand side via some type of lasso. Okay, thank you. This is fine. Thank you.
Next we have Edward, on the alternate respondent.
Very much, Irene. For those of you who are new to AQ, obviously we have a slightly different format than a typical economics conference where the discussant also presents the paper. I just want to point out that was about the most perfect discussion presentation that you can have. So not only did she present our paper extremely clearly, focusing on the highlights. Second, she provided really insightful and useful advice on how to make our paper better, and we really appreciate that. We have the time and ability to implement those. And third, did you notice that she had 4 slides promoting her own research related? So she got her own paper into this as well. That is brilliant. And related, it wasn't an unrelated thing, so that was all great. I do want to acknowledge my co-authors, Partha, who's here, and Jeff Wildridge and Jeff Zabel, who could not be here. So again, first of all, thank you. We really appreciate your clear presentation and comments and suggestions. So let me just comment on a few of the many comments you had. We had not explicitly put into our paper 2 of the 4 assumptions you put, but we agreed that those make sense to state the SUFO or stable unit treatment value assumption, and that the covariates X evolve exogenously separately from the treatment. I have more to say about the covariates in a moment. Your insight about this testable implication we think is really good. That is, the difference in average outcomes over pre-treatment periods across groups should be proportional to the difference in covariates over those pre-treatment periods. That seems like a good insight and easy to implement, as you said, and we should be able to do that. So that's great. We think that would be a great thing. I didn't put this in slides, but 2 other things I wanted to comment on. We did actually compare Flex with the Bourgeois with repeated cross-section, and they are identical. So the imputation method of Bourgeois et al. Is identical numerically to Flex. Flex, we think, is a little easier to do because it's a single regression instead of a multi-stage process, but you get numerically identical results. And the idea of extending this to Poisson would make a lot of sense, particularly with Jeff Wildridge as a co-author. That's an inside joke. If you know Jeff at all, he loves Poisson. So a little more about the covariates. You'd asked whether covariate effects could differ between groups at the same time period. Yes, we can allow for that heterogeneity, and there should be a way to test for that. Time-varying covariates, as you pointed out, are really important in this paper. And covariates are just inherently a little more complicated in a repeated cross-section than in the panel. So I want to stop here and just focus on two basic ways that the covariates might differ within a group over time. The first is just variation due to a random draw of a different set of folks from cross-sectional variation. So even if the underlying population of that group is perfectly stable period after period, if you just take a random draw from that very stable population, you get slight differences in the characteristics of that population, even for covariates that should be perfectly time invariant and would fall out in a true panel. So there's that kind of variation that particularly if you have relatively small numbers per group, you may want to allow for a cross-sectional variation when you wouldn't in a panel. And then there may be some covariates that truly change over time, and then you need to think carefully about why those covariates might change. Is it because of the outcome? If it's a job training program, you're looking at income, then that's clearly endogenous and a problem. If you're looking at health outcomes, health status on the right-hand side, is that due to treatment effect that is the dependent variable? So you're going to think a lot about which variables truly satisfy the third assumption. So the bias variance trade-off that Irene mentioned is something we've also thought about quite a lot. I guess one way that I think about this, Flex allows for the possibility of including covariates additively or interacted with treatment effects. That doesn't mean you have to do that. It does mean you should think about it and figure out which covariates actually make sense. Can this be guided by theory? Can it be guided by what is time varying and or endogenous or so forth? In our experience, throwing in lots and lots of covariates additively plus interactions has not resulted in large standard errors of the treatment effects. It just hasn't. Exactly why we're not entirely sure, but that sort of trade-off, which we initially thought was going to happen, has not happened, not only in the two examples that are in the paper, but in all sorts of other simulations and other data sets that we've looked at. However, we think that some sort of regularization, lasso, or other things could be a good idea for future research to really think about this, which interaction and covariate should be included. You pointed out that one of the things that I think fascinated you most was the idea that the treatment effects tended to shrink, I would say towards zero, not to zero. It's a big difference there. It's not like they all shrank and got incredibly small. There was a movement towards zero, either from positive or from negative towards zero, whenever we added covariates and interactions. Again, not only true for the two examples in the paper, but in many other examples we did. We noticed this. We do not know why. You think theoretically, if you have omitted variables, depending on the correlation with the treatment effects, it could go either way. We always noticed the movement was always in the direction of zero, but definitely not to zero. So that remains an open question. And finally, you gave us a lot to think about with your forecasted average treatment effects. Fate, perhaps, instead of your acronym. That's up to you, but this is clearly complementary work, and this could be really important not only for our paper, but for other different div papers as another way to kind of test assumptions and look at. So we think this is complementary work, and particularly, I think when the time periods are especially long and you can get better estimates of the forecast, we think this could be a really good thing to look into. So thank you for your work on that. And we'll look into that further. So those are my responses. Thank you very much.
Thank you. They are managing their time very nicely, so we have time for questions. There are 2 microphones. Anybody? I'm shy here.
I think it might be a somewhat unfair question, but if we add time varying covariates and that changes our impression, should that make us worry?
If you add time varying or invariant?
Time varying, right? You're saying they have to
Yeah.
be exogenous. And so if we add exogenous covariates, they change our confidence interval substantially. Should that tell us that? Like, can that
Change the confidence intervals or the betas or the?
either, just like if it matters?
I think that's very context dependent on what are the do you think that they ought to be? Presumably that would only happen, at least for the betas, when they are highly correlated with the treatment effect. And then you need to think about what's going on. Is it endogenous the wrong way? Or is there some sort of heterogeneity by that covariate, which you perhaps do want to model? In which case that would be really important.
Thank you.
Anybody else? Missing anyone? Yeah. Yes, we have.
A very interesting result. When I saw you initially, saw it initially presented, I was concerned about getting just a blowing up the number of parameters. In the work you've done so far, if you think of X variables, there being K of them and G being the number of groups, what's the product of K and G in the models you've been looking at? I would worry about the high K values with small g.
Yeah, in the examples we've done, we've had modest numbers of covariates. I mean, certainly in some regression contexts, you could have hundreds of explanatory. I mean, you with your trillions of observations and what you do with Medicare data, you have a lot of degrees of freedom. We haven't gone anywhere near there. And so we've had pretty modest numbers of covariates. And then the other things to consider for treatment effect interactions would be the number of groups and the number of periods. So again, for all 3 of those, and what we've done have been fairly modest. We've looked at examples where the treatments are at the state level. So you have some number of states, sort of half a dozen to a dozen states having treatment. And then sort of up to 10 years of treated years, and then maybe half dozen or a dozen covariates, but which is pretty modest. Yeah, does that answer your question? Right. Okay.
I thought I had a question, but I think I'm okay.
Thank you. So I was wondering, can you comment a little bit on the comparison between your estimator and Botosaru? I know you said in response to Irene that even in the case of repeated cross sections and time varying comparisons, they are identical. So, so is there anything more you would say about so identical in terms of the tau, GT is a little, and also in terms of all aggregate parameters?
So that in terms of the parameters that are estimated, it's numerically identical. And then with aggregation, you can aggregate, there could be different ways of aggregating, but the point is that the point estimates are numerically identical. So there's no difference between this way of estimating a linear regression if you set it up correctly and the Berezjiak way.
So there wouldn't be any specific pros or cons versus doing yours versus Botosaru.
Correct. Numerically the same. Yeah. Exactly the same. I want to say I anticipated that question.
Yeah.
Yeah, there was something about the other colleagues in the group. I imagine those groups which towards the Irene, like, but I cannot imagine we going with the same, so but she, I know what the answer is to that. I was interested in where G fix.
G fix.
G fix, that's like every construction, you're taking 50 states, multiple, but inside the groups N should be big, so I think that's not mine.
Just if I can respond to Irene, so just a recollection that we have thousands of covariates in our regressions. We're in the thousands range with sample sizes of about 400,000, 500,000. And much to our surprise as well, kind of thinking that, okay, we're going to see all kinds of problems. I think the key is that even though you have thousands of covariates and hundreds of treatment effects coefficients, you never report more than 10 or 12, right? So you aggregate it up to the group level, you aggregate it up to the time level, your event studies sort of plot, or you aggregate it up to one number. And that averaging helps clean up a lot of things you might see that you might worry about if you looked at it coefficient by coefficient. I am sure there are coefficients that are completely absurd, right? There must be standard errors that are completely absurd, but they will also occur in places where effective sample sizes are very small, right? Small group effect, so you average, and that saves it a lot. We were surprised.
You wanna say?
No, I was just going to the conversation. I think when people look at this asymptotics with large numbers of covariates, usually it's the ratio of n to k. It's not the k growing, it's n to k. So if n is big, so it's just the number of observations per parameter. So if you have enough observations per parameter estimated, you're good to go. So that if you have 100 observations and 10 parameters, that's probably very bad. So it's just the n to k ratio.
And just to clarify what Partha said, it's not that we had 1,000 covariates to start with, added them in, and then interacted each of those 1,000 with each of the treatment effects. It's by the time you interact a modest number of covariates with all of the G's, all of the time periods, then you can get into the thousands.
Good, we are early, 5 minutes, so either we keep the conversation or have to break for, well, enough that you get some coffee, tea, and come back to your chair because it's only 5 minutes. So it's again